Calculate the dipole moment developed when an electron moves from one atom to other. Across a bond length of 1 angstrom. Now the charge of one electron is 1.6 into 10 raised to power minus 19 coulombs, and 1 angstrom is equal to 10 raised to power minus 10 meter.
So it should be 1.6 into 10 power minus 29.
Coulomb meter.
Yeah.
Mu is equal to magnitude of charge separation into r vector. Now here this mu becomes equal to 1.6 into 10 raised to power minus 19 coulomb multiplied by 10 raised to power minus 10 meter. This is equal to 1.6 into 10 raised to power minus 29 coulomb meter.
Yes, sir.
Clear?
Yeah.
Okay. Next, what would be the value in CGS unit? CGS unit, the electronic charge is 4.8 into 10 raised to power minus 10 ESU. And 1 angstrom is 10 raised to power minus 8 centimeter.
Yes, sir.
Okay.
Yeah.
Now what they found is that this 10 raised to power minus 18 ESU centimeter will always be included in dipole moment measurement.
Yeah.
Okay. When it will always be included in dipole moment measurement, then in that case, what they did was they made this 10 raised to power minus 18 ESU centimeter as a unit.
Okay.
So this 10 raised to power minus 18 ESU centimeter was called a unit, and this unit is known as 1 dBi.
Yes, sir.
Clear?
Yeah.
So this dipole moment actually becomes 4.8 dBi.
Okay, sir.
Clear?
Yeah.
A simple question. What is the value of 1 dBi? What is the value of 1 dBi in SI units?
Sir, it's one electron into one Armstrong into something like this.
What's the value?
Uh, 10 power 11 into 1.6.
Hold on. Rohan, what you can simply do is, I just wanted the value of 1 debye in SI units. So
Okay.
why could you not just equate 4.8 debye to 1.6 into 10 to the minus 29 coulometer?
Oh, okay. So we equate 4.8 debye.
With
So sir, we
1.6
4.
into, we get the value of 1 debye in SI units then.
Okay. So it's 4.8 into 10 power minus 18 then.
What is that?
4.8 in 10 to into 10 power minus 18.
No. 4.8 debye is equal to 1.6 into 10 to the minus 29 coulomb meter.
Okay.
So 1 debye would be equal to how much?
Uh, 1 by 3 into 10 power minus 29.
That would be 3.33 into 10 to the minus 30.
Yes, sir.
Is that clear?
Yes, sir.
So I get the value as 1d is equal to 10 raised to power minus 18 ESU centimeter, which is equal to 3.33 into 10 raised to power minus 30 coulomb meter. Is that clear?
Yes, sir.
Okay, now, having talked about this, now Rohan, one thing you can see very clearly here, what you can see here clearly is that we are talking about the transfer of electron from one atom to the other. If we are talking about the transfer of electron from one atom to other, then in that case, we are talking about the ionic bond and not the covalent bond.
Okay.
Is that clear?
Yes, sir.
Now, if you're talking about the ionic bond and not the covalent bond, then in that case, it simply means that dipole moment which we are going to measure are going to be always less than these predicted values.
Okay. So, but how?
Because the entire electron is not going to actually transfer. We are talking about the partial difference in the electronegativities. We are not talking about huge difference in electronegativity. We are not actually talking about ionic bond. We are talking about covalent bond.
Okay.
Okay. So this value, which we have just calculated out here, is for 100% ionic bond. Whenever we have a covalent bond, it is going to have a lower value than this. It's not going to have so much high value.
Okay.
Okay. Now, if it's going to have a lower value than this, then in that case, the measured dipole moment can actually give us what is the percentage ionic character. So if we talk about the percent ionic character, percent ionic character is equal to the observed dipole moment divided by the calculated dipole moment multiplied by 100.
Yes, sir.
Is that clear?
Yeah.
So this is what we have as the percentage ionic character, that is observed dipole moment divided by calculated dipole moment into 100. Okay.
Okay.
Now write a question. Question is, for a molecule AB, the observed dipole moment is 1.5 dBi and the bond length is 1.2 angstrom. Okay.
Yes, sir.
Consider one electron transfer. Consider one electron transfer and calculate the percent ionic character.
Sir, I got something like 1.5 by 6.4 into 100.
Yeah, solve it.
Okay, okay. Sir, 2.344.
2 point.
34.
Solve it once again. It turns out to be something around 26%.
Oh. Sir, you get mu calculated as 1.92 into 10 power minus 29, right?
Hold on. Here you can just get along with either you can just convert it into this value,
Yeah,
okay,
yeah, yeah, yes, sir.
or you can just get it into the ESU centimeter only. 1.5 divided by is 1.5 into 10 raised to power minus 18 ESU centimeter divided by 1.2 angstrom and 1 electron chain, that is 4.8 into 10 raised to power minus 10 multiplied by 1.2 into 10 raised to power minus 8. Rohan, somehow you got the value right, but you did the calculation wrong.
Oh,
This actually goes off and you are left over with 1.5 upon 4.8 into 1.2 into 100.
oh,
Getting the value.
yes, sir.
So what's the answer now?
Sir, some 27.
Yeah.
Okay. Yes, sir.
Clear?
Yes, sir.
Okay. So that's what we have as the things. Now, we have just talked about the dipole moment, its value, its ionic character. Now, we need to remember that this dipole moment is actually a vector quantity. Now, vector
Yes, sir.
quantities can be added, they can be subtracted, and they can give a resultant. Is that okay?
Yes, sir.
The vector quantities can be added, can be subtracted, they can give a resultant. Now, if we have these vector quantities, we would say, let's say we talk about some molecules. A very famous molecule that we did was BeCl2. Do you remember its shape?
Yes, sir. In line.
It's a linear shape. Cl,
Yeah.
Be, Cl. Now what we find is these two bonds are exactly identical. Now if these two bonds are exactly identical and this has an angle of 180 degrees, these two dipole moments should also be identical. Here
Yes, sir.
there would be a dipole moment. Here there would be a dipole moment. This is mu, this is minus mu.
Yes, sir.
Okay. Now BeCl2 will have polar bonds, but BeCl2 is going to be non-polar. Did we write the
Okay.
definition of polar bonds?
Yeah, yes, sir.
Okay. Now BeCl2 is going to be non-polar molecule. Did we write the definition of polar molecule?
Mm, no, sir. Wait
Write it.
one second. Okay.
Okay, have you written the definition of polar molecule?
No, sir. I didn't try.
Okay, right. The definition of polar molecule. A molecule in which the molecule in which the dipole moments, the dipole moments of various bonds the molecule in which the dipole moments do not completely cancel out so that
So the molecule in which the dipole moments.
do not completely cancel out dipole moments do not completely cancel out so that there is a net resultant dipole moment is termed a polar molecule. Is termed a polar molecule.
Yes, sir.
Okay. Now BCl2, although it has polar bonds, still it will be turning out to be a non-polar molecule because the dipole moments exactly cancel each other. Again, we have a compound like CO2. CO2 again is a linear molecule, and here it's 180 degrees. The dipole moments are exactly equal and opposite. So here also the net dipole moment comes out to be 0. Here again it's come out to be 0.
Yes, sir.
Clear?
Yeah.
Then again, we could have an example of BF3, something like CH4, something like PCl5, something like SF6, something like IF7. Could you just check out what the dipole moments of these molecules would be?
Yes, sir.
Check it out.
So for BF3, the fluorines on the sides would cancel and the one on the top would have a mu.
There isn't any fluorine on the top.
Oh, wait, wait. Yeah, yeah. So mu is 0 for BF3.
Yes, it would be 0.
So even for CH4, mu should be 0.
Yes.
So for PCl5 also mu is 0, right?
Yes.
Yeah. So for IF7 and SF6 mu is 0.
IF7 also mu is 0.
Yeah, sir, because they should cancel, right?
Yes. So all these molecules, the mu is equal to 0.
Okay.
Okay. Now let's talk about another molecule. And that's another famous molecule called NH3. Now if I make the structure of NH3, it is going to be nitrogen along with this hydrogen, 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 and a lone pair. Now if I talk about the dipole moments, here the dipole moments are going to be one is in this direction, another one in this direction, another one in this direction. And importantly, there would be a fourth one in this direction. That is from nitrogen nucleus to the nitrogen lone pair.
Okay.
Now these dipole moments are going to add up and it's going to make ammonia a highly polar molecule.
Okay.
Is that clear? So ammonia is a highly polar molecule.
Yes, sir.
Okay. Now let's talk another example. NF3. Could you just tell me whether NF3 would be having a dipole moment higher or lower than ammonia?
So it should be equal to ammonia.
Check it again. Make the dipole moments.
Sir, opposite in that direction, right?
Yeah, they are opposite in direction. So
So NH3 should be less than NH3.
which one has higher, NH3 or NF3?
So NH3.
Would be higher because in case of NF3, the dipole moments actually cancel each other. They're opposing each other.
Yeah.
In case of NF3, the structure again is similar to NH3. Structure is similar. But when we talk about the dipole moments, in case of NF3, these three dipole moments are this way, and this way, while this dipole moment is here.
Yes, sir.
So dipole moments actually apart cancel each other, and that is why NF3 has a small dipole moment in this direction. NH3 is more polar than NF3.
Yes, sir.
Okay. Now, we can talk about something like H2O. In case of water, we have this and we have two lone pairs. So again, when we talk about water, water has even a lower angle as compared to ammonia. So in case of water, again, we have four dipole moments. 1, 2, 3, and 4. And it has even a higher dipole moment than ammonia. Is it clear?
Yes, sir.
That is why water is polar. So could you give me an answer? Simple answer. And that question
Yes,
is,
sir.
why is water polar? Tell me, why is water polar?
So because the diagram, so it's very highly polar.
So you have to write the answer, isn't it? Could you just
Yeah.
write and speak the answer to me? Why is
Okay.
water polar? Make the diagram also, that is important.
Yeah. So in water, the dipole moments do not cancel each other
The
as
water
they are in the
has
same
a
direction.
non-linear structure. It has a bent structure where the dipole moment do not cancel each other and add.
Yeah. Yes, sir.
That is why water is polar.
Yes, sir.
Okay. Now, Rohan, just do a little thing. You have many examples with you of molecules.
Yes, sir.
Could you just tell me which of these molecules are polar and which of these are non-polar? I think it should not take you more than 5 or 6 minutes.
Okay.
Okay, please do it. We did the table and we did all the examples. You could use that table.
Yes, sir. So the
The VSEPR table.
yeah, yeah. So H2 is polar, right?
H2?
Is non-polar.
H2, yes, it's non-polar. But H2, why did you
And
talk about H2? That's not there in the table.
okay, okay. So that one.
Yes, that one.
Sir,
Yeah.
for the BeCl2, CO2, and N2O,
N2O
they're
is not
not polar.
non-polar. N2O is not non-polar.
Sorry, NO2 plus.
NO2 plus would be non-polar.
So, and sir, SO3, BF3, C2H4, CO3 2 minus, and CH3 plus are non-polar as well.
Yes.
Sir, O3 is
Polar.
non-polar.
O3 is
Polar.
polar.
Okay. So anything with a lone pair is polar, and anything without a lone pair is non-polar, right?
What did you say?
Anything with a lone pair is polar,
Not
and
necessarily.
anything,
Not necessarily, Rohan. That's why I asked you to do it. Otherwise, I would have given you the rule myself.
yes, sir.
N2O. N2O didn't have the lone pair, but still it was polar.
Yeah,
You have to make out the dipole moments and cancel them.
yeah. Sir, and NO2 minus is polar.
NO2?
Minus.
Yes, it would be polar.
Sir, SO2, Cl2, will the oxygens be on the sides?
SO2Cl2 is going to be polar. It's going
Oh,
to be pyramidal.
yeah. Yes,
SO2Cl2 is going to be tetrahedral, but it's going to be slightly polar. The oxygen
okay.
and chlorine dipole moments are going to cancel each other.
Yes, sir. Sir, ClO3 minus is
Polar.
polar. Sir, is xenon more electronegative than oxygen?
No less.
Okay. Sir, SCl2 has to be non-polar.
Mm-hmm.
Okay.
Which one?
Sir, SCl2.
SCl2 is polar. It has two lone pairs. It's like water.
Oh. Sir, is SF4 polar?
Yes, it is.
So there is XeOF3 polar
XeOF.
3.
There is no XeOF3. It should be XeOF2.
Oh, okay.
Yes, it's polar.
Yes. So SiF6 2 minus is non-polar as well.
X.
SiF6 2 minus.
It's not SiF. Yeah, it's non-polar.
So MF6 3 minus.
Mm-hmm.
So is that non-polar?
LF6. ALF6.
So no, sorry, MF6 3 minus.
M. There isn't any M. It is ALF6 3 minus.
Okay, 1 minute. So is XeF4 polar?
XeF4, no.
So it's non-polar.
Yes, XeF4 is planar. There are two lone pairs opposing each other and the fluorines are planar. So you got an example where there is a lone pair but it's non-polar.
Yes, sir.
Okay. I3 minus again would be non-polar. XeF2
Yeah.
would be non-polar.
Yes, sir.
Okay.
Yeah. Yes, sir. I'm done.
Okay. So Rohan, we are gonna have the next class and we are going to finish off the chapter in the next class on Tuesday.
Yes, sir.
No, today is Tuesday.